16.3 Absolute Value Equations and Inequalities. Remember that the definition of absolute value means distance from zero. So, for example, the absolute value of x means the distance that x is from zero. So if we had the absolute value of negative 5 is 5 units from zero. The absolute value of positive 5 is also 5 units away from zero. So absolute value is always going to be a positive answer because you can't have, because distance is always positive, so you can't have a negative distance. And we're going to be using this definition and the examples in this section to set up absolute value equations and inequalities. So before we start looking at the examples, we're going to go through the different types of problems that we're going to be looking at. So the first one is the absolute value of ax plus b equals k. So your problems will be in this form. And when you see a problem in that form, there's two things that you're going to do to set it up, two parts. So I branched them out. And the first one is you're going to set it up as ax plus b equals negative k, or ax plus b equals k, positive k. So notice that on this side, you're basically writing the same thing, dropping the absolute values. On this end, you're writing the same equation, setting it equal to the negative value. Your solution after you solving for x is always going to just be two numbers. So in this case, we're just using p and q to represent it. And usually we don't graph solutions to equations, but if you were to graph it, it would just be 2 points on the line. So when you're asked to write your solution set, you're just going to write the solution set of the set of two numbers that you found. If you are following along in the book with this diagram is on page 1164 in the blue box. If you're writing this on paper, this would be a good place to pause it and copy this diagram, because I'm going to be referring to it over and over again, but I'm not going to be copying it down over and over again. So it'll give you something to look at as we go through it. So the next scenario is where we have ax plus b is greater than k. So this is another type of problem that you'll be seeing. The absolute value of ax plus b is greater than k. When it's greater than k, then you're going to write it one time where ax plus b is greater than k, the same thing, dropping the absolute value. The second one is going to be ax plus b is less than negative k. So you have to flip the inequality symbol to less than and then set it to negative k. So when you do your solution set, and remember this is going to be an OR problem just like the first one. So when you're setting it, writing the solution set, you're going to graph it, and you're going to have from negative infinity to p, and then from q to positive infinity, and your solution set will show that also. So notice that your graph is going to have the left part and the right part shaded with the middle part empty. So I would also either copy this down or just make a note of where that is. That's case 2 in the blue box on page 1164. And this is your third scenario, and I would write this one down also. If you're looking at the blue box on 1164, it's case 3. So this is where we have ax plus b is, the absolute value of ax plus b is less than k. So the case 2 was greater than k, this is less than k. So again, just like all the other ones, one of your scenarios is going to be ax plus b is less than k, so it's going to be the same thing as the original without the absolute value. The second one is going to be ax plus b is greater than negative k. So again, you have to flip the symbol to greater than and set it to the negative. So when we do this, this one's the AND, so the case 1 and case 2 were OR problems. This is an AND problem, which is the intersection. The first two were unions. So since this is an intersection, you're going to graph it and see only where they overlap, which would be in the middle from P to Q. So it's one of those between problems that X is between P and Q. And so your solution set is going to be the interval notation of P and Q. Also notice if you have a less than or equal to some symbol and greater than or equal to, that you're going to have brackets instead of parentheses. So just be careful with the notation that you use. So example 1 on page 1163 says graph the solution set of each equation or inequality. So the absolute value of x is equal to 3. I'm going to take two scenarios, and that's going to be x is equal to negative 3 or x is equal to positive 3. So I just take the positive and the negative. So I'm going to graph that. So I'm going to have negative 3 and positive 3. And since it's an equality, it's equal to, there's nothing really to shade, it's just those 2 points. So my solution set is going to be those 2 points, negative 3 and positive 3. B is the absolute value of x is greater than 3. So I'm going to have x is less than negative 3, so I have to flip it for the negative, and x is greater than 3, and greater than is an or. So then I'm going to graph that. So x is less than negative 3, which is going to be this way, and or greater than 3. And or is a union, so it's just all of that combined. So then when I do my solution set, it's going to look just like this with the union symbol in the middle. So it's going to be negative infinity to negative 3, or 3 to infinity. So the union of negative infinity to negative 3 and 3 to infinity. C is the absolute value of x is less than 3. So my first scenario is x is greater than negative 3. So you flip it with the, you flip the symbol with when you put the negative. And this one is and, so it's an intersection. X is less than 3. So when you keep the same number, you don't have the negative, then you keep the symbol the same. So now I'll graph it. I'm going to have negative 3 and 3. So x is greater than negative 3, and x is less than 3. So where they intersect is this middle section. Okay, so I'm going to redraw my graph. Shading just the solution. So then my solution set is just going to be negative 3 to 3. And remember, that's an interval solution, it's not an ordered pair. Example 2 on page 1164 says solve, check, and graph the solution set of each equation. So A is the absolute value of x plus 2 equals 3. So it's an equation, so we're using case 1, which means that I'm just going to set it to x plus 2 equals negative 3 and x plus 2 equals 3. So I'm going to solve for x on each of these. Alright, so my two solutions are negative 5 and 1. and it says to check, so we're going to plug them back in. So if I have negative 5 plus 2 equals 3, the absolute value of negative 3 is 3, which is true. And then I also have 1 plus 2 equals 3. So the absolute value of 3 equals 3, which is true. Okay, so that's my solution set. And then to graph the two solutions, since it's an equation, it's just going to be a point on negative 5 and a point on 1. And that's all you have to do to graph equations. B is the absolute value of 3x minus 4 equals 11. So I'm going to write 3x minus 4 equals negative 11. And 3x minus 4 equals 11. So we'll solve for x. So we get x equals negative 7/3 and x equals 5. And we will go back and check them. So 3 times negative 7/3 minus 4 equals 11. So these 3's cancel. So negative 7 minus 4 is negative 11. So the absolute value of negative 11 is 11. That's true. And then 3 times 5 minus 4 equals 11. So that's 15 minus 4. So the absolute value of 11 equals 11. That's true also. So my solution set is negative 7/3 and 5. And then I'll graph that. Example 3 on page 1165 says solve, check, and graph the solution set of each inequality. A is the absolute value of x plus 2 is greater than 3. So greater than my constant. We're using case 2, which means that I'm taking x plus 2 is less than negative 3, or x plus 2 is greater than 3. So we'll solve for x. So I got x is less than negative 5, or x is greater than 1. So here's my negative 5, here's my 1, or represents the union. So less than negative 5, greater than 1. So my solution set is going to be negative infinity to negative 5, then union 1 to infinity. Example B is the absolute value of 3x minus 4 is greater than or equal to 11. So I'll write 3x minus 4 is less than or equal to negative 11. So flip the symbol for the negative. And then 3x minus 4 is greater than or equal to 11, which is the same as the original. So we'll solve for x. So I get negative 7/3 and 5, and this is an OR question, a union. So I'm going to graph that. So I have my negative 7/3 and 5. Since it is less than or equal to, I'm going to use brackets, and less than is everything to the left. Greater than or equal to 5, so I'm going to use brackets and shade everything to the right. So that's going to be my graph, and then my solution set will be negative infinity to negative 7/3, union 5 to infinity. Example 4 on page 1165 says solve, check, and graph the solution set of each inequality. So example A is the absolute value of x plus 2 is less than 3. So remember, when we have less than, we're going to have x plus 2 is greater than negative 3, and x plus 2 is less than 3. Okay, so this is the one that's the intersection, the one where the original problem has less than. So we'll solve for x. So my solutions are x is greater than negative 5 and x is less than 1. So when I graph this, greater than 5 is this way, less than 1 is this way. So the overlap would just be the middle part. So then my solution set is just going to be negative 5 to 1. Example B is 3x minus 4 is less than or equal to 11. So we'll write this as 3x minus 4 is greater than or equal to negative 11. And 3x minus 4 is less than or equal to 11. And it's an AND question, which is the intersection. Okay, so solving for x gives me x is greater than or equal to negative 7/3, and x is less than or equal to 5. So greater than or equal to 7/3 is a bracket. I'm going to be shading towards the right. Less than or equal to 5 is a bracket shading towards the left, so they would intersect in between them. So then my solution set will be negative 7/3 to 5. Example 5 on page 1166 says solve the absolute value of 5x plus 2 minus 9 equals negative 7. Check your solutions. So the first thing we need to do is get the absolute value part by itself. Okay, so in order to do that, we're going to add the 9 to both sides. So we have absolute value of 5x plus 2 equals 2. Okay, once you have the absolute value part by itself, then you can solve it like we did the previous examples. So this would be 5x plus 2 equals negative 2, and 5x plus 2 equals 2. And then we'll solve for x on both. So solving for x gives me x is equal to negative 4/5 and x is equal to 0. And before I box my answer, I'm just going to check the solution. So I'm going to plug both of those into x. So for the first one, I have 5 times negative 4/5 plus 2 minus 9 equals negative 7. So I'll work inside the absolute value. So the 5's cancel. So I have the absolute value of negative 4 plus 2 minus 9 equals negative 7. The absolute value of negative 2 minus 9. The absolute value of negative 2 is 2. And 2 minus 9 is negative 7. Okay, so then I'll check the other one, the solution 0. So the absolute value of 5 times 0 is 0 plus 2. So then 2 minus 9. And so that one's correct also. So my solution set is negative 4/5 and 0. Example 6 on page 1167 says solve each inequality and graph the solution set. So A is the absolute value of x plus 2 minus 3 is greater than 2. So again, first thing I'm going to do is get the absolute value part by itself. So I'm going to add 3 to both sides. So I have the absolute value of x plus 2 is greater than 5. So now I'll break that up into two parts. So x plus 2 is less than negative 5. X plus 2 is greater than 5. So greater than is case 2. So this is going to be an OR question. So we'll solve for x. So I have x is less than negative 7, or x is greater than 3. So when I graph it, less than 7, greater than 3, or is a union. So my solution set will be negative infinity to negative 7, union 3 to infinity. B is the absolute value of 3x plus 2 plus 4 is less than or equal to 15. So again, we'll get the absolute value part by itself by subtracting 4 from each side. So that gives me the absolute value of 3x plus 2 is less than or equal to 11. Less than is case 3. So this is going to be 3x plus 2 is greater than or equal to negative 11, and 3x plus 2 is less than or equal to 11. So this is an AND problem or an intersection. So we'll solve for x on both inequalities. So we get x is greater than or equal to negative 13 thirds, and x is less than or equal to 3. So on my graph, greater than or equal to 13 thirds is going to shade that way, and less than or equal to 3 is going to shade that way, and is going to be the intersection. So this solution set will be negative 13 thirds to 3. When solving equations such as the absolute value of ax plus b equals the absolute value of cx plus d, you're going to break that up into two equations, being ax plus b equals cx plus d, or ax plus b equals negative cx plus d. And notice the negative is outside the parentheses of the whole cx plus d, so when you're solving it, you'll have to distribute that negative to each term. Example 7 on page 1167 says solve each equation. So a is the absolute value of k minus 1 equals the absolute value of 5k plus 7. So I'm going to rewrite that as two equations. The first one being k minus 1 equals 5k plus 7. And the second one, k minus 1 equals negative 5k plus 7. So we'll solve each one for k. So solving for k gives me negative 2 and negative 1. And this is going to be a union or an OR question. So my solution set is just going to be negative 2 and negative 1. So example B is the absolute value of 4r minus 1 equals the absolute value of 3r plus 5. So I'll write that as 4r minus 1 equals 3r plus 5. 4r minus 1 equals negative 3r plus 5. So I'll distribute the negative so that this is negative 3r minus 5. And I'll solve both equations for r. So I get r equals 6, or r equals negative 4/7. So since that's a union, my solution set is just going to be negative 4/7 and 6. Example 8 on page 1168 says solve each equation. So A is the absolute value of 6x plus 7 equals negative 5. Well, going back to the definition, remember we said the absolute value of a number is the distance from 0, and it's always positive. So right now, without even solving anything, if this says the absolute value equals a negative number, this is automatically going to be no solution, because you can't have a negative for an absolute value. So if your absolute value is ever equal to a negative, then it's going to be no solution. Now notice that this is when the absolute value is already by itself. Example B is the absolute value of 1/4 x minus 3 equals 0. Well, normally we would put the expression in the absolute value set to the positive or the negative. Since 0 is not positive or negative, you just have the one equation to solve, which would just be 1/4 x minus 3 equals 0. So solving for x gives us 12, so in this case we only have the one solution, which is 12. Example 9, we'll be looking at solving special cases of absolute value inequalities. So 9a gives us the absolute value of x is greater than negative 1. So whenever we have the absolute value greater than or equal to a negative, this is always going to be true, because like we said earlier, the absolute value always has to be greater than 0. So for the absolute value to be greater than 1, that's always going to be true. So it's going to be negative infinity to infinity. For B, the absolute value of x is less than negative 5. Well, this goes back to absolute value having to be positive. So absolute value cannot ever be less than negative 5, because everything less than negative 5 are negative numbers. So this is never true. So it's going to be the empty set. C is the absolute value of x plus 2 is less than or equal to 0. Well, we know that the absolute value of x plus 2 cannot be less than 0, because less than 0 would be negative, and absolute value can't be negative. However, it can be equal to 0. So x plus 2 equals 0. So x is negative 2. So my solution set would be negative 2. And example D, the absolute value of t minus 10 minus 2 is less than or equal to negative 3. So I first need to get the absolute value part by itself, so I'll add 2 to both sides. So I have the absolute value of t minus 10 is less than or equal to negative 1. Well, less than or equal to negative 1 are all negative numbers. So since the absolute value cannot be equal to negative numbers, this is the empty set.